Hello, this is Dr. Nair again, and we are going to work on chapter 4. I am going to divide this into small sections, and in this first part, we will introduce the cycloalkanes, talk a little bit about naming, and also the isomerism that it shows. So, in the last chapter, we saw open chain compounds. However, in this chapter, we are going to deal with organic compounds which contain ring, because many of the cyclic molecules that we encounter in the pharmaceutical or biomolecules like proteins and lipids, and we see that they incorporate this cyclic structures. So, for example, this is a structure of prostaglandin, which is one of the hormones that controls several physiological functions in humans. So you can see that it contains a 5-membered cyclic ring in addition to the side chains here. Another example is the steroid, that is cortisone. Here again you can see that there are several rings, four rings. A couple of them or 3 of them are 6-membered, and one of them is a 5-membered ring. Okay, and again, proteins and lipids and carbohydrates and nucleic acids also incorporate the cyclic structures. So we'll start by seeing how to name them. They have the general formula CnH2n, and in comparison to the normal alkanes, they are short of 2 hydrogens. So the general formula of alkanes is CnH2n plus 2. This is CnH2n, and you can take a comparison here to see that if for the same number of carbon atoms, we have less number of hydrogen atoms when it is taken the form of a ring. For example, this is a propane open chain. When you make it into a cyclic structure, it is called a cyclopropane. And see, we had 8 hydrogens in propane, and now we have only 6 hydrogens. So look at the next one. This is butane, normal butane, C4H10, but here we have C4H8, which is the cyclobutane. Same thing goes with cyclopentane and cyclohexane, which are 5 members and 6-membered rings respectively. So in addition to that, for naming the cycloalkanes, the rules are pretty much the same as we did in the previous chapter. That is, you first find the parent, you count the number of carbon atoms in the ring, and then number the largest substituent. Okay, so if the number of carbon atoms in the ring is equal to or greater than the number in the substituent, then the compound is named as a alkyl substituted alkane. Okay, we'll come to that in a little bit, but here if you see, we have 2 substituents, so you can start either way at either of the substituents. However, once you put the number 1, then you have to make sure that the other substituent gets a lowest number. So in this case, you are making this number 1, so then 2, 3, you have to go clockwise in order to give the lower number to the methyl group here. Okay, so this will be called as 1,3-dimethyl cyclohexane. If you look at this one, you are so this is the incorrect way of naming, that you do not go anti-clockwise, otherwise you will be giving a higher number to the second methyl group. Okay, this is again different ways by which you can name a cycloheptane. However, 2 of them are incorrect ways of doing it, because you are giving higher number to the second substituent or the third substituent. Okay, so if you look at, this is the correct way. So you're going anti-clockwise. In this case, you're going from 1 to 2 to 3, 4, because that way you can give the lowest number to all the substituents. A few more examples here. This is a cyclohexane with 3 substituents. Here we are highlighting the importance of putting them in alphabetical order. So bromo comes first, and then ethyl, and then methyl. So even though you numbered 1, 2, 3, 4, 5, 6 in this way anti-clockwise, you will always place the substituents in alphabetical order. This is a side branch chain, and you can call it as a sec-butyl cyclobutane, or you can separately give a nomenclature to the side chain like 1-methyl propyl cyclobutane. The third one is a pentane, cyclopentane, and it's here again alphabetical order: 1-chloro, 3-methyl, 3-ethyl, 2-methyl cyclopentane. Okay, let's try to name these. This is some examples. Now here you have two substituents, and this is a cycloalkane. So you can number from either side, but in this case, since there are two of them, you have to go alphabetical order. So this one is a isobutyl, okay, and this one is a sec-butyl. So iso falls first in the alphabetical order, so this will be 1, 2, 3, 4, 5, and 6. So this will be named as 1 isobutyl, 3 sec-butyl cyclohexane. The next one is the scenario where we said that if the number of carbon atoms in the largest substituent is greater than the number of the carbons in the ring, so then this becomes your parent chain, and the cyclic ring becomes your substituent. Okay, so in this case, you can number from this side: 1, 2, 3, 4, 5, 6, and 7. So you are giving the second and third position to the methyl group. So it's 2,3-dimethyl, 6-cyclohexyl. Now this becomes cyclohexyl, and since it is a 7-carbon atom chain, it will be a heptane. And so the cyclic ring becomes a substituent here. The next one is an example where we have two substituents, and again alphabetical order. This will be isopropyl. So you will go by this numbering: 1, 2, 3, 4, and 5. So 1 isopropyl, 3-methyl cyclopentane. I have the answers on the next page. So as I said, this is 1 sec-butyl, 3 isobutyl cyclohexane. And this one is 6 cyclohexyl, 2,3-dimethyl heptane, and 1 isopropyl, 3-methyl cyclopentane. All right. Talking about isomerism for cyclic structures. Now, in many aspects, the chemistry of cycloalkanes is like open chain compounds, like normal alkanes. They are all nonpolar and they are fairly inert too. However, there are some important differences, and one main difference is that the cycloalkanes are less flexible than the open chain alkanes. Okay, so if you recall, open chain alkanes, we were able to do different conformations because they have the carbon-carbon single bond. But in this case, they have the single bond, but then their rotation is restricted because of the cyclic structure. So cyclopropane, for example, must be in a very rigid plane here, and if there's no bond rotation allowed here. Okay, but as the number of carbon atom in the chain increases, the freedom of rotation increases. So for example, carbon atom rings which are 25 carbons or up, they are very floppy and they can almost behave as aliphatic alkanes. They do show a type of isomerism which we call it as stereoisomerism, because now since they are cyclic structures, they can have a top phase and a bottom phase. So when the so based on that, based on how the substituents are oriented, either both at the top phase or both at the bottom phase, they will be called as cis. And if one of the substituent is up and the other is down, you call it as trans. Okay, so for example, if I ask you to draw 1,2-dimethyl cyclobutane, and then I say this is a cis, okay, cis 1,2-dimethyl cyclobutane, then the way you will draw it is you draw the cyclobutane, and since it is 2-methyl, these are the 2-methyl, but they are cis to each other. That means they are in the same phase. So you can use this either the wedged bond, or you can use dashed bond, but they both should be on the same face. So either both wedged or both dashed to refer to them as the cis configuration or conformation. If it is asked for a trans 1,2 dimethyl cyclobutane, then you will draw a cyclobutane first and then put one of the methyl groups up and the other down, which could be interchanged, like this one could be down and this one could be up, but that will represent a trans 1,2 dimethyl cyclobutane. Okay. So these type of isomers, we call them as stereoisomers, and they differ from constitutional isomers because in constitutional isomers, the order of the connections was different, right? Or you had different functional groups. But in this case, they are only differing in their spatial arrangement. See, these are both up, one is up and one is down. So these are what are called as stereoisomers, and cis and trans is actually an example of stereoisomers. Okay, so under stereoisomers we have more types. However, this one is the cis-trans isomerism, which is a kind of stereoisomers. We can continue our discussion for the stability of cycloalkanes and ring strain in our next video.